Swayam Prabha. Digital India. Educated India.
A logical and a systematic approach to solving organic chemistry problems for CSIR-NET. In module 20, we will be looking at pericyclic reactions, mainly electrocyclization, cycloaddition, sigmatropic rearrangements, and other concerted reactions. I am Professor Balaji, currently working at Jawaharlal Nehru University. This project is sponsored by DTH Swayam Prabha, MOE, New Delhi. In this session, what we are going to learn is mainly focusing on the pericyclic reactions, that too on electrocyclization, cycloaddition reactions, sigmatropic rearrangements, which will be the major area we will be covering. Along with that, some other concerted reactions. Let us move on to the first problem. So this problem was asked in December 2011. The major product A and B in the following reaction sequences are. So here an aldehyde is given that is reacted with the CBr4 and triphenyl phosphine in the presence of excess of butyl lithium, gives intermediate A, and that intermediate A on treatment with phenyl and copper sulfate sodium ascorbate leads to the formation of B. So these are all the two reactions that are given, and there are four combinations of products are given. The first option has dibromo alkene as intermediate A, and B is having two acid groups in their final product, and in the second option it is just alkene, bromoalkene, with the product is also the second intermediate B is acid derivative, alkene acid derivative, and the third one it is given as a allene type compound, and the final product is 1,2,3 triazole derivative, and the fourth option is an alkyne, and the final product is again a 1,2,3 triazole derivative. So four different options are given. We are going to see what are all the products that will be formed, that is intermediate A and intermediate B. So if we look at how the reaction will proceed, the reaction of CBr4 and triphenyl phosphine is to produce a phosphonium halide. So addition or excess of triphenyl phosphine is getting converted to phosphine oxide, and one molecule or one equivalence of triphenyl phosphine reacts with the CBr4 to give the phosphonium halide compound as shown here, and this phosphonium halide reacts with the aldehyde, the given aldehyde, and this reaction is a well-known Wittig reaction. So the reaction of phosphonium halide with aldehyde is called the Wittig reaction, which gives the corresponding alkene derivative. So this product, in this particular case, we are ending up with a 1,1-dibromoalkene as a product first step, that is the intermediate A, and this on treatment with N-butyl lithium, the first step is the exchange of lithium bromide exchange takes place, and which is followed by the alpha elimination to afford a carbene intermediate. So this carbene intermediate as shown here is the one which will be formed, which is quite unstable, which immediately undergoes a 1,2 shift, that is the hydride ion is shifted, and we end up with a alkyne derivative. So this is the overall reaction, that is a conversion of an aldehyde to an alkyne, and this reaction is called Fritsch-Butenberg-Wischel rearrangement. And then the next step is the overall reaction is called the Corey-Fuchs reaction, and the rearrangement alone is called the Fritsch-Butenberg-Wischel rearrangement. And once the alkyne is formed, the next step is the reaction with the acid, and this reaction is a very famous click reaction, and here we are using copper catalyst. So this is going to give a specific, that is only one of the regioisomers will be formed in this particular reaction. So the reaction or between an alkyne and an acid is called the 1,3 dipolar addition, and this leads to the formation of a 1,2,3 triazole derivative. Since we are using copper, we are going to get only one regioisomer as shown in this reaction. So the overall step is basically the dipolar addition is the one which is the crucial step in this one. So the obtained product, the intermediate A, is the alkyne, which will be the first one that is given here, and this 1,2,3 triazole is the final product that will be formed in the B. So the option D is the correct one for this particular problem. And when we move on to the next problem, so here this question was again asked in December 2011. The major product formed in the following sequence is, so here we are given a alpha beta unsaturated carbonyl compound which is heated to give intermediate A, which is a dimer, and this is treated with sodium borohydride in methanol, that is the reduction is happening, and then the next step is treatment with the paratoluene sulfonic acid, that is the acid treatment. So we end up with the compound B. So there are 4 different options are given here where we may get what is A and B. So these are all the intermediate that are given in this reaction, and let us look at how the reaction will actually proceed. So if you look at the first step is nothing but a dimerization reaction, that is a concerted dimerization reaction or a Diels-Alder reaction. The starting material is the methyl vinyl ketone. This dimerizes to give the intermediate A as shown here, and we have a carbonyl group here, and this carbonyl group on reduction with sodium borohydride gives the corresponding alcohol derivative. And once the alcohol is formed, the next step is treatment under acidic condition, that is PTSA or paratoluene sulfonic acid is used. So this is mainly the proton source. So when the proton source is there, actually what happens is a lone pair of electron from the oxygen is shifted between carbon oxygen bond, and this alkene bond actually takes that proton. So we end up with a oxonium ion as the intermediate, and once we have an oxonium ion which is electropositive in nature, and oxygen being an electronegative compound cannot keep the positive charge for longer time, and there is an oxygen, that alcohol is having a lone pair of oxygen, so this will attack the electrophilic alkenic carbon with the double bond polarizing towards the oxonium ion. So this leads to the cyclization reaction, and we end up with the diazo bicyclo 3,2,1 octane derivative as shown here. So this is the product that will be formed as the final one. This is the product B that will be formed. So if we go back to that our starting one, so this option 2 is the one which is the correct answer for this question. So here we have the carbonyl group which is present as the first step, that is the dimerized product, and the final one is after the reduction and cyclization reaction. So let us move on to the next problem. So this question was asked in December 2012. So the following transformation reaction involves, so there is a aldehyde is given, and then amine compound, secondary amine is also given, alkenic secondary amine is given, and this undergoes certain reactions, and we end up with the final product. So here there are various combinations are given, that means what are all the reactions that will be forming. The first one is an iminium ion formation, so that is the step 1, and then the intermediate undergoes a 3,3 sigmatropic shift followed by a Mannich reaction. So this is one type of reactions that will proceed to give the final product. In the second option, a nitrinium ion is formed as an intermediate which again undergoes a 3,3 sigmatropic shift and the Michael addition to give the final product. And in the third option, there is an iminium ion is formed, and it undergoes basically 1,3 sigmatropic shift and the Mannich reaction. And the last option is a nitrinium ion intermediate and the 1,3 sigmatropic shift followed by Michael addition reaction. So let us look at what are the various reactions which are given, and based on that we have to deduce what could be the possible options that will lead to the final product. So when we talk about iminium ion, what is an iminium ion? Iminium ion is generally formed from amine and a carbonyl compound. So here we have an aldehyde, we have a amine. So that means there is a possibility that an iminium ion can be formed. And what is the next one? That is a sigmatropic shift. A sigmatropic shift generally involves 6 electrons, and it proceeds generally suprafacially. So we will see what is the suprafacial reaction. And the next one is the Mannich reaction. Mannich reaction means it's basically a 3-component coupling reaction which is catalyzed by an acid. And here an aldehyde or ketone reacts with a primary or secondary amine to produce a beta amino carbonyl compound. So this is a Mannich reaction. And when we talk about the next option, which is a nitrinium ion, so nitrinium ion is nothing but a divalent electron deficient nitrogen atom, and the Michael addition is basically a 1,4 addition reaction. So here enolate or other nucleophile and an alpha beta unsaturated compound reacts to give a carbon-carbon bond with the carbonyl groups at the beta carbon atom. So this is what if we have an alpha beta unsaturated system. Here the nucleophile adds to this particular carbon. So this is the beta carbon from the carbonyl group. So and because we consider this as the alpha carbon and this as the beta carbon, so here the nucleophile will add. So this is what is called basically the nucleo 1,4 addition or a Michael addition. And what is the last one, which is the 1,3 sigmatropic shift. So this is basically a thermal hydrate shift is generally forbidden both antrafacially and suprafacially, and the carbon shift requires very high temperature. So these are all the two things we have to remember. So based on that, what we can actually say is that 1,3 shift, whatever the options are given, may not be the right option for this particular transformation. So we can rule out options C and D in the first two options. So we are left with the A and B only, and we will have to see what is the final step, because whether it is a Michael addition or it is a Manich reaction, that is a crucial one that will determine what is the final product which we are going to get. And of course, if you are going to study about sigmatropic shift, there is a website which is given by Tim Wallace from University of Manchester. So he had elaborately talked about the entire 1,3 shift and 3,3 and various other sigmatropic rearrangements. So you can actually read and understand the reactions in a much better way. So if we are going to assume here, because various options are given, and let us assume that the first step is the iminium ion formation. So here we have a secondary amine, we have electrophilic carbon on the aldehydic unit. So these two undergo condensation reaction to, that is a nucleophilic addition to give the product, and this has the nitrogen is having a positive charge, which is because nitrogen is basically electronegative. So having a positive charge on nitrogen is a little bit unstable. So this hydrogen will be lost as a proton. That means the NH bond will be broken towards the nitrogen atom, so that we end up with a neutral charge on nitrogen atom. So this is the first loss of proton, that is deprotonation leads to the formation of a aminal derivative. And once the aminal is formed, the next step is reaction with an acid. So when the aminal is there, there is a hydroxy unit here, and this is basically protonated. And once it protonates, then what will happen is basically to neutralize the charge, and a lone pair of electrons from the nitrogen is shifted towards here, and that leads to the loss of water molecule. So that is the place where we end up with the iminium ion. So there is also another question you may ask, why not this hydroxy unit can also be protonated or not? So this is because we have two hydroxy unit, and the question will obviously arise, why we protonate this hydrogen, this hydroxy unit first and not the other one. So the simply if the hydroxy unit is also protonated, what will happen is it cannot be lost as a water molecule very readily. So that is one of the reason, even though there is a hydrogen atom here and this will form, but when this particular alkene is formed, that is not going to lead to the formation of the iminium ion. So because in this particular case we are mainly focused on the formation of iminium ion, so here we will be mainly focusing on the loss of hydroxy unit from the aminal unit, which is adjacent to the amine. And this intermediate, that iminium ion, is never isolated because it's quite unstable, and this iminium ion only can undergo 3,3 azacope rearrangement, that is the 3,3 sigmatropic shift is the next step that is given. So even though the other isomer can also be formed, we are mainly focusing on this particular iminium ion because that is how the next step is given in the question paper as one of the option. So this iminium ion undergoes 3,3 azacope rearrangement that leads to the intermediate as shown here, and this one can now readily undergo the Manich reaction because we have a enolic unit that is present here, and this enolic unit can form the Manich reaction, and we end up with the final product, that carbonyl compound as shown here. So this is where the whole steps of reaction, that is the first step is the iminium ion formation, followed by the 3,3 sigmatropic shift, and the final reaction is the managed reaction, is the correct option for the conversion of the starting aldehyde to the final product that is given here. So option A is the correct answer for this particular question. And let us move on to the next problem. So here, this question was asked in December 2013, and the major product A and B formed in the following synthetic sequence is a carboxylic acid is given, and this is treated with thionyl chloride and triethylamine and vinyl ether. So these are all the three steps that are carried out on the carboxylic acid, and four options are given as expected product, but we don't know which one is actually going to be the right one that will be formed in this reaction. So we have to work out how the whole reactions will be proceeding. If you look very carefully, carboxylic acid when treated with thionyl chloride will be getting converted to a acid chloride. So that is a very obvious reaction. And the treatment with the triethylamine, this is a little bit tricky, and we have to understand how this reaction actually proceeds. So if you know what is the product that will be formed, that is mainly in this particular case, we are going to end up with a ketene. And the next step is ketene is going to undergo a reaction with the vinyl ether. So that is going to be some concerted reaction. And then we have 2+2 addition, that is what actually going to happen. And we may end up with either one of these two products, either A or B. We are going to see what is the actually the correct product, because C and D are ruled out because the last step is actually a 2+2 cycloaddition reaction. So here we do not have a 2+2 cycloaddition product. So that means C and D are completely ruled out in this particular case. So how the reaction actually proceeds is the first step is the conversion of the acid to an acid chloride, which is very straightforward reaction. And in the next step, the triethylamine actually abstract an acidic hydrogen atom. So that leads to the formation of the concomitant loss of the chloride unit also happens in the single step. So that leads to a quite unstable ketene intermediate. So this is the crucial step in this particular reaction. And so once the ketene is formed, the next step is the reaction of the ketene with the vinyl ether. So this is nothing but a simple 2+2 cycloaddition reaction. So when a 2+2 cycloaddition reaction happens, we end up with a 4-membered ring as the product that is formed. So here if you look at, this is having the final product. So that is the option B is the correct thing for this reaction, and because the ethoxy unit is not lost during that process. So in option A there is no ethoxy unit, so that is the reason option B is the correct one for this particular problem. And when we move on to the next problem, so this was asked in June 2014. A major product is formed in the following reaction sequence. So here we have a nitro compound is given, and this nitroethane is a starting material that is reacted with the isocyanate and the triethylamine, and an alkene is also used. So these are used in two different steps that leads to an intermediate A, and that intermediate A, we have 4 different options are given, and in these 4 options we are going to find out what is the intermediate A and what is the final product B. The intermediate A is treated with hydrogen and ranane nickel, followed by reaction with methanol, water and acetic acid. So these are all the various steps that are involved. So we need to identify what are all the intermediate A and B. If you look at all the 4 products are basically isoxazole derivatives, and the next step is reduction with the hydrogen and ranane nickel. So that will basically cleave that NO bond, and we end up with a corresponding carbonyl unit. So if we look at options 1, 2, 3 and 4, the last step is basically the reduction of a carbonyl unit also may take place during this one, because here the NO bond is actually broken in this reaction. So the breakage of NO bond will lead to a hydroxy derivative and not a carbonyl derivative. So we can rule out 3 as one of our product. Now we have only the option 1, 2 and 4 which could be the possible product. So we have to now find it out how the reaction actually proceeds. So the first step is actually in the presence of a base. The nitroethane or the nitroalkane combines with the positively charged carbon of the isocyanate. Phenyl isocyanate is given here. So this forms an intermediate as shown here. And this is a very simple reaction. The oxide anion attacks the electrophilic carbon atom with the carbon oxygen bond polarizing towards the oxygen moiety. So we end up with a negative charge on the oxygen. And the next step is basically the shift of hydrogen atoms, because here nitrogen is having a positive charge and here the oxygen is having a negative charge. So what can actually happen is a shift of bonds will take place, and this leads to a addition compound as shown here. So this is the addition compound that will be formed, and the same compound can also be formed by an alternate route. That means the nitronate anion, that is we are using a triethylamine as a base. So instead of the oxide anion, the nitronate anion can also undergo the same set of reactions. Here again, it will again attack the positively charged isocyanates electrophilic carbon, and this again will lead to the same intermediate. And this again undergoes the proton transfer. So one of the hydrogen atom is shifted from the alkene carbon to the nitrogen. So this shifts internally, and that leads to the formation of nitrile oxide. So we have the nitrogen here, we have the oxide here. So this is nothing but a cyanide unit. So cyanide unit means nitrile, this is oxide. So this is a nitrile oxide that will be formed, and basically this nitrile oxide is formed from a carbamic acid, and that carbamic acid decomposes to an amine and a carbon dioxide. So the overall reaction is basically called a Mukiyama procedure, because Mukiyama developed this particular procedure, and this was reported in JACS 1916. The reference is given here. And once this nitrile oxide is formed, then the next step is going to be the reaction with an alkene. So here it is a 1,3 dipolar addition that is going to take place. So we have the two heteroatoms that are present, nitrogen and oxygen, and we have a alkenic bond that is also present. So all these things get involved in the 1,3 dipolar addition reaction, which leads to the formation of a isoxazoline derivative in this particular case. So here the trans stereochemistry of the starting material is retained in the final product. So if you look at these two carbon atoms, they both are, the methyl groups are in the trans orientation. So this is one of the clue which exactly tells us how the reaction actually proceeds, because the starting material stereochemistry is retained in the final product. And the hydrogenation of this isoxazoline derivative leads to the opening of the ring. That means the NO bond is actually cleaved, and the oxygen bond is actually getting converted to the hydroxy unit, and we end up with the imino derivative. And this imino derivative can be treated with methanol, and that means basically a hydrolysis reaction takes place, which leads to the carbonyl group. And if you look at very carefully, the oxygen is present on this particular carbon, and these two are in the trans geometry. So if you look at here, the hydroxy unit and the methyl are in the trans stereochemistry. So this is the crucial step we will have to keep in mind while solving this particular problem. And let us move on to the next problem. So here the intermediate A and the major product B formed in the following reaction sequences. So here a couple of steps are given, and this question was asked in December 2014. So this reaction looks a little bit complicated because various steps are involved in this reaction. The first one is a reaction with the TBAF, that is a base in acetonitrile at 50 degrees centigrade. So this is step number 1. And in the step number 2, we have another reaction, very crucial reaction that is happening, and they both lead to the intermediate A. That intermediate A on heating undergoes concerted reaction. We are going to see what is a concerted reaction to give the final product B. So here all the product which are given are little bit multi-cyclic systems. So we are going to look at how each step will actually follow. The first thing we have to remember is whenever we use TBAF, TBAF is actually a very good reagent for reaction or removal of silicon unit. So in the starting material, what is the silicon unit we have is basically a trimethylsilyl unit that is present. So the trimethylsilyl unit is easily removed by a base, that is tertiary butyl ammonium fluoride. So the TBAF base has a very strong tendency to react with the silicon, and most of the deprotection reactions involving silyl ethers are generally carried out with TBAF. So that is the first one that leads to a anion formation on this particular carbon atom. And since we have multiple bonds, alkene bonds, double bonds which are in conjugation, so what happens is a shift of the electrons takes place that leads to the nitrogen being more nucleophilic in this particular case. So and we have a electrophilic carbonyl unit that is present in the second reactant. So the reaction actually proceeds as shown here with the concomitant loss of the carbonyl unit, and this ethoxy carbonyl ester is being attacked by the nucleophilic, that is the immunonitrogen attacks that ethoxy carbonyl esters carboxyl unit. So that leads to this particular intermediate. And if we look at this compound, we have an alkene double bond here, we have another double bond here, we have another double bond here. So there are 3 double bonds that are present in this compound. So if we actually rearrange or write the structures in a little bit different way, what we can have is all these 3 double bonds can come in close proximity. So that leads to a Diels-Alder reaction, 4n plus 2 pi electrons cyclization. That means this is a suprafacial concerted reaction that is actually happening between the 4 pi electrons and 2 pi electrons. So here these are all the 4 pi electrons and this is the 2 pi electrons. So these two undergo a Diels-Alder reaction and we end up with a cyclized product as shown here. So this is the overall reaction that is taking place. The crucial thing is the formation of this Diels-Alder adduct. Let us move on to the next problem. So here the major product formed in the following reaction is we have a hydroxide derivative that is given here, and this undergoes various steps to give what is the intermediate that will be formed in this particular case. We have 4 different options, A, B, C, D are given, and we are going to see how each step will proceed. And this question was asked in December 2014. So the first step is treatment with an acid chloride. So that acid chloride in the presence of triethylamine, generally what happens is we have an acid chloride, we have an alcohol. So these two will react to give an ester. And the next step is reaction with LDA and then TMSCl. So TMSCl is generally used for the protection of hydroxy units. We are going to see how hydroxy compound will be formed in this reaction. And then the next step is heating of that intermediate, whatever is formed, followed by the reaction with the acidic conditions. So acidic conditions may cleave acid ester group or similar type of groups. And the last step is basically a diazo reaction. So if you look at carefully, there are various steps which are very crucial we have to remember. And since the last step involves a diazo reaction, that means introduction of a methyl unit to the product. So if you look at option A, there is no methyl unit. So that means option A can be completely ruled out. And in B, we have COET. So there is no methyl unit in the product. So that means B also can be ruled out. And we have only C and D, both have a, and again C is also ruled out because we have a carboxylic acid, and D only has a methyl ester. So even without looking at or even going through each steps, we can easily figure it out. The correct option for this reaction is going to be D only, because that is only having the methyl ester, because the last step is the diazomethane reaction. Diazomethane reaction is generally used for the conversion of acid to a methyl ester. So let us look at how the reaction actually proceeds. So we have a hydroxy unit which is treated with the acid chloride that leads to the formation of acyl derivative. So this is a simple reaction, and then the treatment of LDA, actually this generates, this abstracts the most acidic hydrogen atom. So here we actually had the hydrogen atom which was removed by the base. LDA removes this hydrogen atom to give an anion on this particular carbon. So once we have an anion and we also have a carbonyl group adjacent to that, it's going to form a enolate which is quite stable intermediate and at low temperatures. And this enolate is now treated with the trimethyl chloride. So that basically converts the corresponding carbonyl unit into a enol silyl ether. So this is the ene and this is the ol and this is the silyl ether. So enol silyl ether is the one that will be formed when the treatment of this corresponding acyl derivative with LDA and TMSCl. So once this is formed, the next step is basically going to be the 3+3 cyclization reaction. So that leads to a rearranged product as a alkene double bond is formed here with concomitant loss of the silyl enol ether, that unit is entirely lost. So we end up with a double bond on this particular system, and here also we have a, this particular unit is getting converted to the silyl ester, and this silyl ester is hydrolyzed using an acidic condition which gives a carboxylic acid derivative, and the carboxylic acid derivative on treatment with the diazomethane gives the corresponding methyl ester. So that way the option D is the correct one, and we can easily figure it out in this reaction even without going through all the steps. Next problem is the major product of the following reaction is, here an alkyne and carbon dioxides are given in the presence of a nickel catalyst. That leads to a cyclic product. So this question was asked in June 2015, and here three options are given, that is A, carbon dioxide combines with the catalyst, that is option number 1, and in the second option insertion of CO2 occurs, and in the third option insertion of the alkyne takes place. So these are all the three options given, and the correct answer is A and B, or B and C, C and A, or A, B and C. So any combination of the options A, B, C are possible. That is what is given, and let us look at how the reaction actually proceeds. So in this particular case it is a single step reaction. So we have a alkyne, two alkyne units and the carbon dioxide. All the three reacts together in a 2+2+2 fashion, that is a 2+2+2 cycloaddition reaction happens in the presence of the metal catalyst. Okay, so the correct option for this one is B and C. Here the insertion of the carbon dioxide unit takes place, so that is correct, and the insertion happens between the alkyne units. So B and C are the correct options, which leads to the final product as shown here. So this is how we can easily figure it out in this particular reaction. The crucial step is the 2+2+2 cycloaddition. Let us move on to the next problem. The correct combination of reagents to effect the following reaction is, so here we have a starting material and it's a dialkene, and this is treated with potassium hydride and 18 Cron 6 at room temperature to give an intermediate A, and that was treated with phosphonium ylide and n-butyl lithium at -20 degree, 0 degree. That leads to a final product B. So these are all the two things which are given here, and this question was asked in December 2015. So the first step is a crucial one, because here some sort of cycloaddition reaction happening, and that leads to some intermediate which reacts with the corresponding phosphonium ylide to give an alkene derivative. So if you look at all the combinations which are given as 1, 2, 3 and 4, all of them the starting material, that means the intermediate A, have an aldehydic unit. All the 4 are having that, and also in the second intermediate, that is B, what is the difference is only in some of the cases the stereochemistry is the only thing that is different, and in the first case the product's stereochemistry is also changed between option 1 and 2 or option 3 and 4. So this is the stereochemistry of the alkyl groups. Similarly, the stereochemistry of the double bond. These are all the only options that are changed in this reaction. Now we have to figure it out which one is the right combination, that is A and B. So the first step is basically the starting material undergoes a 3,3-oxacope sigmatropic rearrangement. So this is the crucial step. So that leads to the formation, because here we had given a 6-member transition state. So this 6-member transition state is the crucial one for the concerted reaction to occur, and that leads to a enol derivative. So here we have the enolic derivative that is formed in this reaction, and the driving force for this reaction is basically the cyclohexane chair conformation in the transition state. So that is the reason this 3,3-oxacope rearrangement happens very readily. And in the next step, the enol is a little bit unstable. So this tautomerizes to the aldehydic derivative. So this aldehyde is formed, and this aldehyde can be drawn as shown here, and which can also be drawn as shown here in this particular case. So here both the methyl groups are in the cis geometry, and in the final step we have an aldehyde, and aldehyde is treated with a phosphonium halide in the presence of a base. This is nothing but a simple Wittig reaction, and the only thing is here we are using a unstabilized halide. So when we are using an unstabilized halide, that actually leads to the formation of Z alkene. So both the hydrogens are on the same side, or we can also call this as a cis alkene. In this particular case, since the substituents are different, we call this as an Z alkene. So this is the crucial one we have to remember. Whenever we use an unstabilized halide, that always leads to the formation of a Z alkene. Let us move on to the next problem. So here the major product A and B formed in the following reaction sequences. So an alkene-alkyne derivative is given here, which is treated with ruthenium catalyst, that leads to the formation of an intermediate A, which again is treated with a alkene derivative to give a product B. So here we are going to find out what are all the reactions that is happening, and this question was asked in December 2016. So we have various combination of the products that will be formed, and we are actually going to look out whether we can rule out some of the compound that may be formed in this particular reaction. So if we look at the way in which the structure is drawn, here we have actually basically a 5-membered ring which can easily be formed if it undergoes some sort of reaction with the metal catalyst. So if you look at option A, option 1, 2, 3 and 4, option 1 and 2 have a 5-membered ring as the intermediate A, but there is a exocyclic double bond, and in 3 and 4 we again have a 5-membered ring, but this is a cyclobutene type compound. So in other words, if you look at, in both the cases we actually have a 5-membered ring that is formed. So this is a little bit difficult to identify what could be the final product. But when we look at the second step, so here if we look at the option 1, we have a double bond. That means this is very similar to a Diels-Alder diene type compound, and we actually have a alkene given as a second counterpart, dienophile. So we may get a 6-membered ring. So intermediate A getting converted to B through a Diels-Alder reaction is possible for the option 1. The same is also the case for option 2. And if you look at 3 and 4, the 3 and 4, it is basically a 2+2 cycloaddition type reaction. So we have two types of combinations that are possible. One is a Diels-Alder combination, another one is a 2+2 addition reaction. So we have to figure it out, because this is not a very simple or a straightforward reaction where we can easily rule out what options are not possible. So we have to look little bit carefully to find out what is the final product that will be formed. So the first step is basically a 2+2 addition reaction of the catalyst and the alkene to give a 4-membered ring. So the catalyst is basically written here as a M, and instead of writing the entire structures with ruthenium and other thing, we have simply written as the MLN. Ln is nothing but the ligands which are attached to the metal atom. So this first undergoes a 2+2 cycloaddition reaction. So we have an alkene and we also have a double bond. So these two forms the first step of reaction, and once this is formed, now this metal is transferred to the reacting substrate, and a styrene unit is liberated in this particular reaction. So in the starting material, we do not have the metal attached to the starting material, but after the cycloaddition reaction, the metal is now transferred to the corresponding starting material. So in other words, what we do is like an oxidative addition actually took place. So the next step is again an intramolecular reaction between the alkene and an alkyne. So here again there is a 2+2 cycloaddition reaction happening. So that leads to the formation of the cyclobutene ring, so as shown here. And this again loses actually this reopening of this link, this cyclobutene ring, because it's a quite unstable ring. So this opens up to give now the shift of the metal from the alkene unit to this alkyne unit has happened in this particular case. So during the whole process, what happened is we have actually formed a cyclopentene type intermediate that is actually formed. So this is the overall steps that are happening, and here now the metal is attached to the exocyclic double bond, and once this intermediate is formed, again this will undergo a 2+2 addition reaction with the styrene that is liberated in the previous step. So now the styrene comes and this reacts with this particular alkene. So we have a 2+2 addition happening between the metal and the styrene unit. So that leads to a 4-membered ring, cyclobutane ring, and this now liberates or is lost as the catalyst. So now the catalyst is actually regenerated from this material. So we end up with the intermediate A where there is no metal. So what we can say is like the first step is the oxidative addition and the last step is the reductive elimination. So the reductive elimination of the metal catalyst takes place. That means it is regenerated, and now this can undergo the second cycle. So we end up with the intermediate A. So in this intermediate, we have a cyclopentene system with the acyclic double bond. And once this is formed, now as we have talked about in option A and B, we can actually make a 4+2 addition, that is the Diels-Alder reaction. Cycloaddition reaction is possible here because the alkene, the diene is present in the one of the starting material, and in the second step B comes as a dienophile. So we have a 4+2 Diels-Alder reaction, and that leads to the final observed product. So what we can remember is like in the final product, the starting material in the last step has a trans geometry or cis geometry. These two ester units are in the same side. So in the final product also, both the ester units are on the same side. So that is the stereochemistry is retained in the Diels-Alder reaction, and starting cis ester and the final product have the same stereochemistry. So we can say this is the final product B. So that way we can identify this is not a 2+2 addition reaction. The last step is not a 2+2 addition reaction, but it is a Diels-Alder reaction which leads to the final product. Let us move on to the next problem. So here the correct sequence of pericyclic reactions involved in the following transformation is: we are given a alkene. The alkene is treated with selenium dioxide as a catalyst, and tertiary butyl hydroperoxide is also used in this reaction. And the next step is a PCC oxidation reaction. So this question was asked in December 2016. So there are various steps that are given here, and the first one is a ene reaction. We have to identify what are all the possible products. First step is a ene reaction, second is a 2,3 sigmatropic shift, and the third is a 3,3 sigmatropic shift, option A. And option B is first step is a ene reaction, second is again a 3,3 sigmatropic shift, and the last is a 1,3 sigmatropic shift. And the third option is a 2,3 sigmatropic shift as a first step, followed by yin reaction, followed by 1,3 sigmatropic shift. When we talk about the selenium dioxide, we are going to see what type of reactions it will undergo with the alkene as shown here. And the last option D is a 1,3 sigmatropic shift and a 2,3 sigmatropic shift as the second step, and the last one is a 3,3 sigmatropic shift. But as we have seen earlier also, 1,3 sigmatropic shift involving hydrogen atom is a little bit unfavorable kind of things, or it's a forbidden reactions, both the thermal and photochemical reactions. But 1,3 alkyl shift are actually possible, at least superficially, at high temperatures. So based on that, here it is not given whether it is a hydrate shift or an alkyl shift. So we can assume that any one combinations are possible. So let us look at what are the different reactions that are given. Based on that, can we get some clue in this one? So first step is a yin reaction. So yin reaction is nothing but a addition of a compound with a multiple bond, which is called an enophile, to a olefin with a allylic hydrogen. So this is the most crucial one. So we need an allylic hydrogen atom for the yin reaction to undergo. So whenever we have a allylic whenever we have an yin with an allylic hydrogen atom, and when we treat this with a multiple bonded compound, they both undergo yin reaction. The second one is a 2,3 sigmatropic shift. So here a sigma bond migrates across a conjugated system to a new place. Here a 5-membered rings are involved in the transition state. So that's the reason when we say 2,3, so total 5 atoms are basically involved in that reaction. So that is the reason we call this as a 2,3 sigmatropic shift, and the main thing is a 5-member transition shift state. And when we go to the next option, that is a 3,3 sigmatropic shift. So here again the sigma bond migrates, and 3 atoms here, if it is all carbon atoms that are involved, that is called a Cope rearrangement, and if an oxygen is involved, that is called a Claisen-Cope rearrangement. So that is how we can differentiate between 3,3 sigmatropic shift, and when a nitrogen is involved, we call this as a Asa-Cope rearrangement. So depending on what is the heteroatom involved, that Cope rearrangement can be either oxygen involved or nitrogen involved. And 1,3 sigmatropic shift, as we mentioned earlier also, hydrogen shifts are forbidden, both thermal and supra and antrafacial conditions, and photochemical shift is only possible in the suprafacial concerted reactions, and carbon shift is possible for both thermal and and in that particular case we are actually getting an inversion in the stereochemistry. So let us look at the various reaction. We can start with the first option, which is the yin reaction. So here the starting material has a allylic hydrogen, and the reacting second unit, that is the second substrate, has a multiple bond. Here again, this is actually used as a catalytic unit, and we will see why we are considering this as a catalytic unit, and it is not required to be a 1:1 equivalent. We will see that when we move through the reaction mechanism. So the selenium dioxide is a enophile that is involved. The alkene is the ene that is involved in this reaction. So the first step is the reaction of this alkene to the electrophilic selenium center. So this is what is the ene reaction. So here the hydrogen is shifted to this particular oxygen unit. So that is where we end up with this particular reaction intermediate. And how the reaction actually proceeds is basically shown here. And once this intermediate is formed, this will undergo a 2,3 thermal shift, that is 2,3 sigmatropic shift is given. So here we have a 5-membered transition state. Let us start from selenium. 1, 2, 3, 4 and 5. 5 atoms are involved in this particular transition state. So this is the 2,3 sigmatropic shift that happens. So in this particular case, the selenium is actually shifting towards this particular carbon. So here if you look at the double bond is actually shifted. So this is basically the 2,3 shift that is happening. That leads to a allyl selenite ester, and once the allyl selenite ester is actually formed, this loses selenium dihydroxide. So that leads to a allylic alcohol as the final product, and this overall reaction is basically called as a Rayleigh oxidation reaction. And here the liberated selenium derivative is oxidized to the selenium dioxide by the tertiary butyl hydroperoxide that is used. So that's the reason if we don't use the tertiary butyl hydrogen peroxide is not used as a co-oxidant, in those cases selenium dioxide has to be used in one equivalent. But when we use selenium dioxide as a second, when we use potassium, when we use tertiary butyl hydrogen peroxide as a secondary oxidant, this selenium dioxide can be regenerated. In other words, it can be used as a catalyst in this particular reaction. So the next step is the formation of the this allyl alcohol now undergoes reaction with the selenium dioxide to give the ester, and once the ester is formed, this again undergoes a 3,3 sigmatropic shift, that is as shown here, and here the oxygen is involved. So this is a oxycope rearrangement that is actually happening, and this leads to a allyl selenium derivative, and this on hydrolysis gives a E alcohol. So this is the most crucial thing we have to remember. In this particular conversion, the alkene is converted to a E allyl alcohol. So once the E allyl alcohol is formed, the next step is the oxidation using PCC that leads to the corresponding aldehydic unit. So we end up with the alpha beta unsaturated derivative. So this is how the overall reaction actually is happening. Let us move on to the next problem. So the major product formed in the following reaction sequences, we have this question is asked in December 2016. So we don't know what is the starting material. It is given. It is treated with triethyl orthoformate, and a catalytic amount of propanoic acid is used, and this reaction is heated to give some product as shown here. We have to now find out what is the starting material that will be used. There are 4 combinations are given, A, B, C, D. So we have to find out what is the starting material in this particular reaction. So let us look at how the reaction actually proceeds, because even though we don't know what the starting material is, what we can assume is the triethyl orthoformate actually undergoes various reactions in the presence of a catalyst. So the first step is actually the protonation of one of the ethoxy unit in the starting material. So once it is protonated, the oxygen actually gets a positive charge, which is quite unstable. So this is lost as a ethanol unit as the first one. So we end up with the oxonium ion intermediate, and oxonium cation is formed, and again we have the alcohol which is coming into this picture. So the alcohol actually reacts, rather it attacks the electrophilic carbon unit, and then we end up with this corresponding derivative. The acetal is actually formed, and once this is formed, what it undergoes is it again loses another ethanol unit. So we end up with the corresponding oxonium ion, oxonium cation, that is again formed in the next step. Once this oxonium ion is formed, this can actually exist in the resonance structures. So once it is having or it is written in the resonance structure, we have a hydrogen atom attached to this methyl unit, which can be actually shifted. That leads to a 1,5-diene intermediate as shown here. So this is a crucial one. Here we have a double bond, here we have a double bond, here we have an oxygen. So what type of reaction it can undergo is basically a Johnson-Clayton 3,3 sigmatropic shift is possible in this particular case. So that leads to a final product, that is the gamma delta unsaturated ester is formed. So this is our final product. So this can be formed only from this particular corresponding alcohol unit. So that is how we can actually find out whether the option A, B, C or D, that is the starting material. So here the stereochemistry of the final product is actually the same as the corresponding alcohol. So this gives a little bit hint for us to figure it out what is the final product that will be formed. And the next problem is the major product formed in the following reaction is. So we have a cyclopentadiene as the starting material. This is treated with cinnamyl esters in the presence of AlCl3 in the solvent dichloromethane at 0 degree. That leads to an intermediate A, and this intermediate A on treatment with ozone followed by sodium borohydride followed by reaction with an acid leads to a product B. So we are going to find out what are all the products intermediate A and B that will be formed in all these 4 combinations. So this question was asked in June 2017. So let us look at whether we can figure it out what could be a possible reaction. So here we have a diene that is present and we have a dienophile. So when we have a diene and dienophile, obviously we can think of a Diels-Alder reaction. So if you look at all the combinations, so option 1 and option 3 are the 2 compounds which are giving the bicyclic derivative, and that could be a probable reaction that is possible. But if you look at option 2 and 4, they are actually 4 can be easily ruled out, because when we have a diene and a dienophile, the obvious reaction is going to be a Diels-Alder reaction. So 4 can be easily ruled out, and 2 also can be ruled out because that's also not a Diels-Alder reaction. So we can think of option 1 or 3 as the final product. And if we look very carefully between option 1 and 3, the the intermediate A is same in both the cases. But in the case of B, the stereochemistry of the phenyl unit is, and again one of the hydrogen are the only thing which are different in both the cases. Now we have to just carefully look at whether we can easily figure it out how this reaction actually proceeds. Now let us look at each individual step. So the first step is basically the Diels-Alder reaction, that is the trans ethyl cinnamate reacts with the cyclopentadiene to give a trans product. So this is the first step, and this undergoes ozonolysis. In other words, this alkene double bond is broken down to give a diol derivative, and this actually internally attacks the ester unit, and that leads to the formation of a lactone derivative. So basically this lactone is actually formed, and if we look very carefully, the stereochemistry is basically the phenyl unit is pointing upwards. So that's the reason we can easily find out how the reaction actually proceeds. So here we have the hydrogen unit is pointing upwards. Similarly, the phenyl unit is also going to be pointing upwards. And let us move on to the next problem. So here the major product formed in the following reaction is, here we are given a bicyclic ring system containing an exocyclic double bond. The first step is reaction with magnesium, carbon dioxide and an acidic workup. The second step is reaction with COCl2, and the last step is reaction with triethylamine. So this question was asked in June 2017. We have 4 combinations that are given, and let us look at what are the product that will be formed, because here it's very difficult to identify what type of reaction are the intermediates that will be formed. So we'll have to work out the reaction to find out. So the first step is we have a bromo derivative. The bromo derivative is undergoing a Grignard reaction with magnesium, and use of carbon dioxide is basically used for the conversion of the halo derivative to a carboxylic acid. So this is the first step that is taking place, and the treatment of this with the oxalyl chloride leads to the corresponding acid chloride formation. So once we have an acid chloride formation, when this is treated with the triethylamine, so this reaction we have seen earlier also, so that leads to the formation of an unstable ketene. So here again the acid chloride will be converted to the unstable ketene, and this unstable ketene undergoes a 2+2 cycloaddition reaction. When we say 2+2 cycloaddition reaction, we end up with a cyclobutanone derivative. So this is going to be the final product that will be formed in this particular reaction. Thank you so much.